Hello everyone, welcome to another short video on solving a LeetCode problem with APL. Yeah, I got that right. For a second there I thought I had said things in the wrong order. So today we are solving problem 1920, build array from permutation. And for some reason this sounds really familiar, so have I not solved this yet? Just give me a second because this number does ring a bell, and so I want to figure out what's going on. Where is it? 1920. Oh, okay, no. So yeah, this hasn't been solved before by me. So let's open the problem statement. And the problem statement says, given a zero-based permutation, build an array of the same length where the answer is the original indexed by itself. Yeah, sure. This is... Oh, I see. This is... This rings a bell because... yeah, on Code Report's YouTube channel, we have seen a solution to this problem. So it's Code Report. If you're watching this video, you actually know that channel because I got a shout out recently. But if you don't know this channel, go ahead and check it out. It's Code Report by Connor Hoekstra. So yeah, he solved this problem and we are going to tackle it as well. I don't know if I recall his solution, so we'll see if we can replicate his solution. So the very first or the most obvious solution in my opinion is, let's define these to be the numbers we are working with. So if we do literally this, we get our solution. So 0, 1, 2, 4, 5, 3. 0, 1, 2, 4, 5, 3. And notice that this is exactly how they define, like they define the answer to be like this, and then they just have to specify index by index because this is a generic, this is like pseudocode. But in APL, we can get away without specifying each individual index, and so we can index an array into itself when the values are legal indices, and so this just works. So our basic solution could be just this. Yeah, and now we can, whoops, if we know how to type, we can get it. Yeah. Now Connor Hoekstra, so Connor used something else. Let's see if I can remember. I remember that he used the indexing primitive, and then he used a nice little fork with it, and it was something like, now I never know how to use this. I think this is the way you do it. Yeah, amazing. Okay, so how does the index primitive work? So you give it an array on the right, and on the left you can give it a single index. And so let's take a look at nums. So this is 0, 1, 2. So the number at index 2 is 1, right? So if I do 2 index into nums, I get the 1. Now, if you have higher, so this nums is a single vector, right? It's a simple vector, but I can make it a matrix. So let's see. If I reshape it like this, now I have a matrix, and I can still use the index primitive to access elements over here. So if I wanted to reach 5, for example, that's on the row number 1 and column number 1. So I can type 1, 1. Yeah. So now what this shows is that typing 1, 1, or for example, if I type 0, 1, can you figure out what's the element I'm picking from this matrix? Well, this is row 0, that's this row, and this is column 1, so that's the number 2. And so this picks the number 2. Now the problem is the fact that this tries to index into to the array, because there's two numbers in here, shows that this expression cannot pick the first and second elements from nums, because this having length 2 means that the index primitive is expecting a matrix on the right, and so this doesn't work. So the way you get around that, in order to have this pick the first two elements, you need to enclose these two elements. And now this retrieves the first two elements of nums. Or for example, if I wanted to pick the 2 and the 5, these are at indices 1 and 3, so I would do enclose of 1 and 3, index into nums. Yeah. And so what I want to do is I want to enclose the whole thing. I want to enclose the whole vector. And this is my solution. And then Connor proceeded to writing this as a fork. As a fork. And so what he did was he figured out, well, having just nums in here is the same as having right tech nums. And then this is the pattern of a fork. It's a dyadic function in the middle with two monadic functions on both sides. So you just extract the functions and you have the argument on the right. So this was Connor's solution. Can we do something else? Yeah, we can. We can use the chipmunk. And this is a chipmunk. There's the eyes over there and these are the cheeks. And then if you have the nums vector on the left and on the right, this also works. And what is this doing? Well, how can I show it to you? Well, this is the... Okay, I can just type it in here. So this is the pick primitive. If you give it just something on the right, it will return the very first thing that you have. So it's used monadically, it's actually called first. But if you give it an index on the left, it will pick that particular element. So now what we want to do is we want to apply this pick primitive to each of the numbers on the left. So we use the each operator. But we want this each to only go over the numbers on the left. We want the vector on the right to be seen as a whole vector. We don't want to traverse over that, and so we enclose it. And that's when we draw this little chipmunk shape. And then, because we don't like repeating ourselves, we can use the selfie operator. And now what this does is it just takes the right argument and puts it on the left as well. So, whoa, what did I do wrong? Oh yeah, right. So this is actually interesting. So what I'm doing here is with the selfie over here. So I was thrown away by the fact that this is colored differently. If you notice, when I complete the chipmunk, this gets a different color, and so I was looking at this as a single unit. But when I added the selfie operator, the selfie binds to this. And so it's actually as if there was something here, and so the selfie here puts nums on the left of the enclose, and so I'm doing this, and then I'm doing the peak of each. And that's why this weird thing comes out, when actually what I want is I want to have the chipmunk, and then I want the whole thing to have a selfie with the nums. Now this will be seen as an atop, so will it work like I want it to? No, it won't. I need this to be a single function, and then this works. Okay, so this may look weird. Just bear in mind that the original thing that we started with was the chipmunk, and then I'm just using some function composition to make this work point free. So I can do something like sol is pick of each composed with the enclose, and then a selfie of that, and now I can do sol nums. Yeah, and let's just check it with the second test case they have in here. So that, now sol with that gives me 4, 5, not 1, 2, 3. 4, 5, not 1, 2, 3. Yeah, that's it. Okay, so these were 3 basic solutions. I hope you learned something. If you have any alternative solutions, feel free to comment down below. I'll leave a link to Connor's video in the description, and I'll see you for the next one. Bye.